This video is completely optional. You are not responsible for this, but some of you may be interested in some of the math behind ordinary least squares and the properties about it. So I had summarized the model here in the course packet, and then we found our ordinary least squares estimators, and I kind of gave you a very quick and concise proof here of that. I'm going to walk you through that in a little bit more detail in this video, and then we're going to try to establish these properties. So the properties about our least squares estimators are that they're, first off, they're unbiased. Secondly, we have certain standard errors. The third one is that they're normal. So how do we do that? So let's go over to my document camera, and I'm going to just kind of put want to show OLS estimates. So we're going to derive the OLS estimates. We want to show that the OLS estimates are unbiased. The variance of these estimates equal sigma squared times x transpose x inverse, and then these estimates are normal. So those are my claims. So in order to do this, I'm going to start out by reviewing the model. So every y is just going to be some intercept plus beta 1 times x. This is going to be I1 plus all the way through beta p xip plus some error e sub I. And what I'm going to assume is that the expected value of these errors are all 0. The variance of the errors are all sigma squared. The errors are normal and uncorrelated. All right. Now, I'm going to start by representing all of this as matrices. So we're going to have a y vector, so y1 through yn. This is going to be y written as a vector. So if I put a little line over it like that, that means it's a vector. And on the right-hand side of the equation, we're going to end up with a matrix that looks like this. I'm going to have a column of 1s. Then I'm going to have my x's. So x1, 1, x2, 1, all the way through xn1. We have ... x1p, x2p, all the way through xnp. And you can put dots everywhere if you like. So this is going to be a giant X matrix. So let's just make this a big X matrix. I'll make it as bold as I can. And sometimes it helps to write down the dimensions. So this is n by 1, this is n by p plus 1. The plus 1 comes from the intercept. Now, I'm going to have a beta vector. So the beta vector looks like this. Beta naught, beta 1 all the way through beta p. So this is my beta vector, which is going to be p plus 1 by 1. Plus, oops, I'm kind of running out of space here, e1 through en. So plus my errors, and this is going to be an n by 1 quantity. All right, and we better stick our equal sign in there. And so hopefully you'll convince yourself that this is a very compact way to write out this equation up here, where I is equal to 1 to n. Okay, so instead of having n equations, I can just write it in this very compact matrix form. All right, let's say that b, okay, b is going to be some vector, is an estimate of my beta, my true beta vector. So then my y hats, so this y hat is an n by 1 vector, is just going to be my x matrix times this b. I'm going to stop sticking my little arrows on top of it. So that's just, my predicted values are equal to that. I can also define my residuals. So my residuals, so this is a residual vector. This is also an n by 1. It's going to be my estimator of this e, is going to be then, well, y minus y hat, or y minus x times b, using the notation that I just established over there. All right, well, that's good. So what's the OLS criteria? So the OLS criterion is minimize the sum of squared errors, so the residual sums of squares. So let's go write out RSS. RSS is, you'll recall, the sum I equals 1 to n of my residuals squared. Now, we can write this objective function very compactly using my matrix notation. This is just E hat transpose times E hat. Now these are all vectors. So if you want to think about this, E hat transpose looks something like this: E hat 1 through E hat n. Then this would be E not transposed, E1 through E hat n. What happens when you multiply this? Well, this is just going to be the sum E hat sub I squared, and that's what I have right here. So I hope that you'll agree that this is a very compact way to write this equation. Now, I'm going to go write out what E hat is. So what E hat really is y minus xb transpose times y minus xb. Now, I'm going to multiply this out. Now, when you transpose this, you get y transpose, and then you permute the order of this. This is an n by p plus 1 quantity. To keep all the dimensions right, this is going to be minus b transpose x transpose times y minus xb. All right. Well, let's go multiply this out. I'm gonna do that over here. This is, if I take the first term, y transpose times y, I get y transpose times y. Now let's take the first term times the last term, so minus y transpose xb. Then let's take the second term times the first, minus b transpose x transpose y. And then the last term is going to be plus, well, b transpose x times b. Now, what's really important to notice about this is that all of these are 1 by 1 quantities. So this is, think of this as a 1 by n, and this is an n by 1, so that's a 1 by 1. This is also 1 by n. This is going to be n by p plus 1 by 1. So this is a 1 by 1 quantity. This is a 1 by 1 quantity. And when you transpose a 1 by 1 quantity, you get the same thing back. So I can transpose either one of these, and that's totally fine. It's going to be the same thing. So with that noted, we can think of this as y transpose y. That's the first term. These two things are really the same. Okay, so this becomes minus 2, and I'm going to use this one, beta transpose x transpose y. And then we have the last term. So plus b transpose x, b. All right, so we've just you know, kind of written out the objective function. So we want to minimize this. Want to minimize this. That's our goal. So how do we minimize something? Well, the answer is we're going to have to take derivatives and set it equal to 0 and solve. So how do we take derivatives? Well, if you go back to the course packet, I gave us a link to the Wikipedia page, and the Wikipedia page shows us how we can do, I call it matrix calculus. So how do you take derivatives of matrices? All right, so you can read through that on your own. I'm going to review a little bit of basic calculus with you. And so the basic calculus is this. You know, let's say I have some function a times x, and I want to differentiate that with respect to x. So what is that? What is the derivative? Well, it's just a. Likewise, what if I had a function like this, ax squared, and I want to differentiate that with respect to x? Well, that's just 2a times x. Now, if you look at your, you know, the Wikipedia page, if x is now, you know, call it a, you know, a vector, and so is a, with the same dimension, then the result is this: the partial derivative of x transpose a with respect to x is just a. So it's almost exactly like what we had before. And the partial derivative of a times, sorry, let me write this, start over again here. The partial derivative of x transpose times a times x with respect to x is equal to 2 times a times x. So it's exactly like that. I don't want to spend a lot, I don't want to dwell on this, but just to kind of convince you of what's happening here. Let's say that you have something like a1x1 plus a2x2. So you can think of this as x transpose times a. So where x is x1, x2, a is a1, a2. If you do the multiplication, you get x1, a1 plus x2, a2. All right. So if I were to take the partial of x transpose a with respect to x1, what is that? Well, it's going to be a1 plus 0. Take the partial of that same thing with respect to x2, you end up with a2, and therefore the partial of x transpose times a with respect to this x as a vector is just a1, a2. All right, so let's go back to what we had before. And so if I want to minimize this function, I need to take the partial derivative of this with respect to my parameter, which in this case is, you know, the b. And what is that? Well, notice that this first term doesn't involve b at all. Therefore, the partial derivative is 0. Just like if we go back to basic calculus, the partial derivative, well, the derivative of a with respect to x is 0. So that's the equivalent of what we're doing here. Now, the second term you're going to see involves just a single copy of b. So it's going to be like this case where you've got a linear function of your parameters. So this is equal to minus 2, that's going to go away, x transpose times y. Now what do we have here? This last term is a big square matrix in the middle, and it's going to be like this one. So it's going to be 2 times that big square matrix in the middle times whatever we're taking the derivative with respect to. So this is equal to this is going to be equal to 2 x transpose x and then times b. So now we've just taken the derivative. I'm going to set this equal to 0 and solve for it. So let's go solve for my unknown, which is that b right there. So I'll move this other term to the other side, so 2, and I'm going to give myself a little bit of space here. X transpose x b has to equal on the other side, the negative becomes a positive, x transpose times y. Now, I can divide both sides by 2, those cross out. I'm going to pre-multiply by x transpose x inverse. So x transpose x inverse. And then what happens is these cross out, and you're just left with b equal to x transpose x inverse x transpose times y. And that is a very important equation. That is the the formula that you compute if you want to find your OLS estimates. So if we go back to what I said earlier, we want to compute the OLS estimates. We've just done that, so we can cross that one off the list. All right, the next thing that I said we were going to do was to show that these things are normal. So let's go establish that they're normal. So what I want you to note is this is equal to, well, x transpose x inverse, x transpose, and then what is y? Well, y is x times beta plus some errors. So I'm going to go multiply this out. X transpose x inverse, x transpose x times beta, plus another big mess, so x transpose x inverse, x transpose times e. Now, those things cross out. I didn't mean to cross out the beta. This is all left equal to beta plus, well, x transpose x inverse, x transpose times e. Now, what do we have here? We have a linear combination. So beta is a constant. This whole matrix here is another constant. All right. And what do we have here? We have a normal random variable. So RV is often used for random variable. So what I see here is that I'm just taking a linear combination of normal E. So if you take a linear combination of some normal random variables, you end up with something normal. So therefore, this tells us B is normal, as long as our errors are normal. So I'm going to go back to what I claimed we were going to show. I claim that I've just shown to you that our B's are normal. All right. Let's go establish the unbiasedness. So what we want to show in order to get to unbiasedness is that the expected value of these estimators equals the parameter beta. So how do we do this? I'm going to remind you of a formula that you should have seen back in basic probability, namely this. E at ax plus b is just a e of x plus b. So you can distribute, you can take a constant out, you can take the constants out of that expectation. And it turns out that you have exactly the same thing with vectors and matrices. So the expected value of a matrix A times some random variable x plus b is just A times the expected value of x plus b. All right, so let's go apply this to our estimator. What's the expected value of beta? Well, I'm going to go copy what I had from before. This is beta plus x transpose x inverse x transpose times e. All right, so we recognize this as taking this form. So this is like this additive constant that I called b over here. This is like my matrix A. This is like that matrix big A. So what are we left with? Well, we're just left with beta plus, well, x transpose times x inverse x transpose times the expected value of E. What's the expected value of E? Well, if you go way back to the beginning, the expected value of E is 0. So this thing is 0, therefore this whole thing is 0. And the answer is beta. So what this is saying is, on the average, your OLS estimators equal the true parameter beta. Okay, so sometimes your estimates will be too high, sometimes they'll be too low, but on the average you get the true value. So OLS is unbiased. So if we come back to what I said I was going to show, I claim that I've just shown that. The last part of OLS theory that I'm going to show today is the variance of it. So we want to find the variance of B. Well, I'm going to remind you of a formula from basic stats. So what is this? So A times some random variable plus B. This is just A squared times the variance of X, is a formula that you would have seen back in a good course on probability, undergraduate probability. All right, well, it turns out there's a very similar version for matrices. So what is the variance of A times some random vector X plus B? So the result is, this is just A times the variance of X, A transpose. So you've got you pre and post multiply that, so it's like you've got 2 copies of A, just like you had 2 copies of A back there. All right, well, let's go try this. So what's the variance of B? This is just going to be the variance of this big messy formula that we had back here. So this is going to be beta plus, well, X transpose X inverse X transpose times E. Maybe I'll make these brackets, square brackets. And what I want you to note is this beta is like this B constant here. And this whole thing, again, is like that big A matrix. And then the errors are the random variables here. So let's go find this. This would be equal to just the A matrix. So the A matrix here is going to be X transpose X inverse X transpose times the variance of E times A transpose. So when we transpose this thing like we did before, we have to kind of permute the order so that X transpose becomes an X. Notice that this is a symmetric matrix, so this is just X transpose times X inverse. That, since it's symmetric, the transpose is equal to itself. Well, what is the variance of E? So the variance of E, if we go way back to the beginning, was just sigma squared. So let me write this another way. The variance of E is sigma squared, which is a constant, times the identity matrix. So the identity matrix, you'll remember, looks something like this. So we could say this is sigma squared times 1, 1, 1, dot, 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 1, and you have a bunch of zeros in the off diagonal. All right, so this is a very compact way of saying the variance of any single observation is just sigma squared, and at the same time, the covariance between any two observations is 0. That's all that off diagonal zeros there. So this is sigma squared times I. So this is a scalar, or just a number, so we can bring that thing out in front. Then we have x transpose x inverse x transpose. Then we get the identity, but that's just like sticking a 1 in there, so that goes away. We just ignore a 1. X transpose x, and then x transpose times x inverse. Notice that these two things cross out. So this is just another copy of I. Multiply something by its inverse, you get I. And so you're left with x transpose times x inverse times sigma squared. And that's the formula for the variance of B. So we have now shown that. What I've just done is derived the main properties of OLS. So, they're unbiased, you got a certain variance, they're normal. The only thing I haven't done is establish that they're the best linear unbiased estimators, meaning they have the lowest variance. So among all unbiased estimators, I can't find an estimator that has smaller variance than the OLS ones. That's a more difficult thing to prove, so I'm not going to do it in this video, but it's kind of the last essential fact to know about OLS estimates. They're BLUE. They're the best linear unbiased estimator. I should probably write that. So BLUE means best, meaning lowest variance, linear, unbiased estimate. All right, that's it for the math and theory of ordinary least squares.